Hello, class. Welcome back. So last time we were talking about orbitals, energies, and how they relate to the quantum model of the atom. So we're just going to jump right back into it. And I think we left off on this diagram here. So this is the general ordering of the individual orbitals, the different types of orbitals. So if you are kind of confused right now, don't worry. We're going to talk about what these mean and how do we fill the orbitals on for like electron configurations. We'll talk about that soon. Okay. So we're talking about orbitals now, right? So what are orbitals? So electron orbitals. So it's better if we write this stuff down so it kind of sticks better in our mind. So electron orbitals. So don't worry too much about the formal definition. We just need to be able to tell which one's an s, p, or d orbital. So orbitals are, they are mathematically described region within an atom in which there is a high probability that an electron will be found. So knowing the exact location of an electron is impossible, so we use mathematics to kind of pinpoint where we think the electron will be in an atom, and that's called an orbital. So I won't go too much about how an orbital is derived. That's not the point of this class. So if you do have questions about what an orbital, like how does it come about, you can always ask me like outside of lecture. All right. So, but pretty simply, that's where we find the electron, and we can solve for these orbitals using mathematics, and then we get a solution. And now we have what we call sublevels. Each sublevel, each sublevel has a fixed number of orbitals that is in increasing progression of odd numbers. Okay, so for example, we have s equals 1, so there's one s orbital. P equals 3, so 3p orbitals. D equals 5. And then F equals 7. So there's no elements where we have found G orbitals, so it stops from at F. So these orbitals are described this way because they are based on mathematics. So it's based on mathematics. Of the quantum theory, and you do not need to know what that is, but just know that we can use math to get these orbitals. Quantum theory orbital shapes are drawn. So the shapes of the orbitals are drawn based on an x, y, and z axes. So a 3D and 3D shape are drawn around x, y, and z axes. So now let's go back to the slide so you can get a better picture of what I'm talking about. Okay, so see this picture here? So this is the Bohr model compared to the quantum model. So now we know in the Bohr model, we assume that the electrons are traveling on these fixed orbits around the nucleus, and they were circular or elliptical, like in space, like the planets around a star. But in the quantum model, what we say is that the electrons, they can be anywhere in that empty space, and we cannot know exactly where that electron is and like the trajectory of it. We just know that due to the positive and negative attractive forces, that the electron should be closely like dense or closely concentrated towards the center, and that's why you see the probability dots here. They're more towards the center where the nucleus should lie. But you see here, it can also spread further and further away apart towards the edges of the sphere. And the quantum theory that states that we do not know exactly where the electron is 100% at any given moment. We can only suggest the probability or position where the electron could be found in the atom. So there's a principle for this, or I don't think we go over it, but it states that you can either know the speed of an electron or how fast it's going, or the position. You can't know both. That's physically impossible. So that's what the quantum model states for where the electron is proposed to be. So the quantum model, it kind of addresses the issues with the Bohr model, because the Bohr model, it fails with multi-electron elements. So after the hydrogen atom, what we use for the Bohr model, we cannot describe atoms of other elements. So we need to go to the quantum model to account for where the electrons are, and they are in what we call orbitals or principal energy levels. Okay, hopefully everyone's is still with me. Let's move on. So here's are the shapes of the orbitals. You'll have to be able to visually recognize. I won't ask you to draw them, but I do expect you to associate the orbital pictures with the type of orbital or sublevel that we have gone over. So first we have the top spherical ones. They are called s orbitals. So they are like spheres, spherical, very circular, and for a set of s orbitals, there's only one. So now we go to the next higher energy level. These are called p orbitals. See here, it has px because it's aligned on the x-axis. Py, this is aligned on the y-axis. It goes through the center of the orbitals. So the p orbitals, they look like dumbbells. That's a common mnemonic to kind of visualize them. And then pz is on the z-axis, so that's why it's coming straight up down right there. There's d orbitals, dz squared. That's they look like this because of the function of the orbital name and the expression. So Z squared is the one that looks like a donut in the center. That one, it kind of gives it away. So that is the one where it's kind of distinct from all the others. Next, you have dx squared minus y squared. So this one is unique because the axes, the x and y axes, the x squared minus y squared, I mean, it goes through the orbital lobes right here. Whereas the dxy, dyz, and dxe, they don't do that. They are situated between the two axes that are denoted here. So for example, xy, it's laying on the xy plane, yz, yz plane. So like this L here, this one is like this flat xy. So it's always lying on that plane. And xz is this guy right here. So this one that's coming out towards us. So it's kind of going like that. So it's always between or on the plane of two axes. Whereas x squared minus y squared, it's on the axis itself, the x and y. So it's kind of if you visualize the x, y, it's on the whole entirety of the cross there, on the cross section in the center there. So I don't expect you guys to draw it. That's something you might have to do in Gen Chem, but not here. You'll have so to prepare for that, you should be able to visually pair them together, or just say, oh, if I gave you one of these orbitals, you should be able to identify that it's a d orbital and not a p or s. But you might have to identify what p orbital is. So that is fair game. So is it px, py, and pz, and hopefully use these tricks to kind of figure it out. Okay, let's go to the next slide. So hopefully everyone got familiar with all these shapes. Okay, so as we move down the periodic table, the sizes of the orbitals get larger because the elements, they have more electrons and they occupy more principal energy levels. So as we go from 1s to 2s to 3s, we can see that the atomic size of the element will increase, and with that, an increasing size of the s atomic orbitals. So always increase as you go down the periodic table. So down a group. Okay, so now let's talk about the Pauli exclusion principle, and I'll explain some particular features for electrons and how we can identify them. Okay, so let's switch gears here. Let's go back to the iPad. All right, so we're going to talk now about the Pauli exclusion principle. So if you guys took chemistry in high school, you might have heard of this, but it's okay if you haven't. We're going to go over it. So the Pauli exclusion principle, what it says is that more than two electrons cannot occupy the same orbital. So what that means is that an orbital has to be occupied by either one electron, unoccupied, no electrons, or two electrons, and no other occupancy is possible. So that is the nature of the electron and the orbitals. So that is the Pauli exclusion principle. So let's go over that. More than two electrons cannot occupy the same orbital. So an orbital may be one unoccupied, so you have an empty orbital, and that we won't talk much about So the fact that an orbital is empty or occupied 1 or 2 electrons, that will give you insight into its reactivity or of an element's reactivity. But we're not going to, don't pay too much attention to that. Just know that it can be unoccupied or partially or fully occupied by 1 or 2 electrons. So unoccupied, occupied by 1 electron, or occupied by 2. Let's just rewrite this. So, and no other occupancy is possible. So you can't have more than 2. Occupancy is possible. Okay, let's move on here. Okay, so now we're going to be talking about the electron configuration and how the stuff we've been talking about, how it relates to the periodic table and what we see the elements and how they're arranged. Okay, so please stick with me. This is going to be a little bit vague, so please follow along as best as you can and make sure to review this video if you have trouble doing this on the homework. So electron configuration. So people may have heard of electron configurations. It's that diagram I showed on the very first slide with those energy levels arranged. So we're going to be using that type of depiction, and we're going to be filling in those energy levels with electrons. So that is what we call electron configuration, and they tell us a lot of detail about properties of elements and of materials, and it can give us valuable information. So electron configuration and periodic table. Okay, so electron configuration, what is that? So it is the orbital arrangement. So I usually do not test on the definition, but it's good to know what it means. It's just the arrangement of electrons in ions or atoms, but I usually test writing electron configurations, either the orbital diagram or the configuration itself. We'll talk about what that is. So orbital arrangement of electrons in ions or atoms. Okay. So there are a few rules that we have to go by. So rules, that guide assignment. Assignment of electrons to orbitals. Okay. So some rules are electrons fill the lowest energy levels. Energy orbitals. Orbitals available at ground state. So at the ground state, we fill the lowest energy orbitals first before we fill the higher ones. So no orbital can have more than 2 electrons. So it's because of this arrangement. So arrangement of electrons by quantum model is the basis. Is the basis for the allocation of elements in the periodic table. So the periodic table, the arrangement of the atoms or elements is all because of these electron configurations by the quantum model. So we can actually see trends in the periodic table based on these electron configurations. Okay, let's move on. All right, so let's share this screen again. So let's go back. So I'm going to show you what I mean here. Okay, so this is our periodic table, remember? So what you need to, you want to kind of visualize is that, visualize is that each block, they represent an orbital where the electrons can be found. For example, the hydrogen atom will have one electron in the s block or the s orbital. And helium will be in the same s block. As you go down here, these two groups of elements will also have electrons occupying the s block. Transition metals will have electrons occupying the d block, so the 3d, 4d, 5d, 6d, and then elements down here will have f block electrons, so electrons in the f orbitals, and right over here is the p block, and that will be electrons in the p orbitals. So study this graph, you will need to be able to write electron configurations based on this information. So any electrons here are in the p orbitals, d orbitals, f orbitals, s orbitals. So s block, d block, p block, and f block. Okay, I think we're going to go over an exercise about this in a bit, but we'll take it slow and go over this very carefully. Okay, so next here is a sublevel energy diagram. So see here, this diagram. So we can actually measure and look at a visualization of a sublevel energy through this energy diagram, and that is pretty cool. So we do have information backing us about the shapes of the orbitals, but you see here how it's circular in nature, and then there's right down there is dead center is looking like that empty space. So this shows us the energy level, the orbital, and where the electron could partially or be expected to be found with some probability. Okay, but don't, this is just related back to what we actually can see. So just know that what we're teaching you does have a basis in what we study. Okay, let's move on. Okay, so let's switch back to the iPad. So let's talk about electron configurations. What do these numbers mean? Okay, so we're going to go talk about that. Okay, so let's talk about notation now. Electron configuration notation. Let me just check the time here. 55 more minutes, so let's keep going. All right, so for example, my hydrogen atom. So here's my hydrogen atom. Okay, now how we represent hydrogen's electron configuration is we write 1s. So that means the principal energy level is the 1, ground state, and the s, the electron is going to be found in the s orbital. And then we use a superscript for 1, meaning that the orbital s is occupied by only 1 electron because hydrogen only has 1 electron. So this is 1 electron in the sublevel. This is the sublevel S. And this is the principal quantum number. Number N. So from this information, we can tell what energy level it's in, the sublevel, which orbital is in, and how many electrons are in that orbital. Okay. So let's go back now to the electron configurations for common elements. So we're going to be looking right here. So on this page, we can see the electron configuration for all the elements. So I probably won't ask you to write electron configurations for anything else besides these, just because I don't think it's necessary to start off with. So these are some you can expect. You might have to write the neutral atoms. So these are just the neutral atoms. I might ask you to write electron configurations for ions, not neutral atoms, but these are probably the ones I will test or you'll be expected to know. So note here that every atom in this row, they all end with the S and 1 electron in the sublevel. So 1s1. As you go down to further elements, you have to take the energy levels that were below it and have them filled because they're filled. And as we go to the highest orbital, that's where the number will max out. So, but there'll be lots of practice with this, especially in the homework. So here's the S block, the D block, and then the P block here. And we'll talk about how to write these out. Okay. So please study this. If there's any confusion on what any of these numbers mean, please let me know and ask questions, email me, or ask them on Piazza. Okay, all right. So how do we write these electron configurations? So we're going to talk about now electron configuration. Neon and argon cores. So when you're writing electron configuration, you can use what we call a neon or argon core to specify that my electron configuration has the configuration of neon or argon, and the rest of the configuration is blah blah blah. This is kind of a shorthand of writing it, and that's what you saw on the previous slide that I showed you. So you can do that when writing these, but I will most likely ask you to fill out an energy orbital diagram, or it could be writing out the configuration. I haven't decided yet. So we have neon core. So electron configuration. So the electron configuration is, so for neon is 1s2, 2s2, 2p6. So if you have a hard time visualizing that, so think about where neon is at the end of the second row. So it has electrons in the first energy level, 1s2, all those electrons, all the electrons in the 2s sublevel, 2s2, and then neon's all the way at the end of the p block for the second level. So we have all the p electrons, so that's 2p6. So neon is what's called noble gas because it has a filled outermost shell. So all these electrons, all the orbitals are filled. So it's really happy as a noble gas. So you rarely see neon participating in reactions because it doesn't need to share any electrons to reach the filled shell state because it's already pretty happy with as neon itself. But anyway, so we symbolize it as this, symbolize as neon in brackets in an electron configuration. Of a species. Of a species with more electrons than neon. So for example, where will we see this? Here's my example here. Say I have aluminum. So aluminum has Al. So make sure you practice with the symbols. Is Z equals 13. Can be expressed as, so we take neon, and then we have 3s2, 3p1. So a good way to know where you wrote the correct electron configuration, you just count the number of electrons in the element. So example, aluminum has 13 electrons. So if we go back here to our neon core, it has 2 electrons from the S, another 2 electrons from the 2s, then 6 electrons from the 2p. So that's 10 electrons. And then it has 2 electrons from the 3s2. That is 2 plus 1 from the p equals 13 electrons. So you have 2 plus 2 plus 6. So this is the neon core. Now you have plus 2 plus 1, and that equals 13 electrons. So we have written the correct electron configuration for aluminum. Okay, so that's neon core. Argon core is much of the same thing, except you're talking about argon now. So here we have argon. Argon is also a noble gas. So electron configuration is, so argon is one row okay, so there's an error on the slide. So argon core is actually this. Okay, so argon is just one row below neon. So it's going to be 1s2, 2s2, 2p6, 3s2, and then 3p6. So on the slides, it has 4s1. That is not correct. That's the electron configuration, I believe, for calcium. So that's not argon. So just erase the 4s1. I'll fix that in the slides and upload it. So it's a noble gas, so it ends at 3p6. So we symbolize it as argon. Symbolized as the argon shell right here, argon core in the electron configuration. Of a species. Species with more electrons than argon. Let me just double check electron configuration for argon. Okay, let's see here. Okay, so the 4s1, the typo we talked about, that's actually the electron configuration for potassium, but don't worry about that. Let's focus on our example here. So our example will be zinc. So zinc has a atomic number of 30. So the example is, but it can be expressed as argon, 4s2, 3d10. So we can also think about counting up all the electrons in the configuration, but you don't have to as long as it's correct. But if you were to count out all the electrons up to the 4s2, 3d10, the number of electrons should match the z, the atomic number, and that'll be 30 in this case. Okay, so hopefully that was okay. In the homework, you'll have lots of practice writing these configurations, but just remember where the S block is, the D block, and the P block. I don't think we'll ever talk about elements in the F block, just because those elements are they have much more niche applications and much more other applications in chemistry that we usually do not talk about. So you'll probably talk about them in Gen Chem, like Chem 2C, but not in this class. So I'll have to wait. Okay. So let's go over the steps for writing an electron configuration in case anyone is confused. So let's go about writing electron configuration. So I recommend you study this because a lot of people do miss it. And I think writing electron configurations is one of the more easiest concepts to encounter. So please study how to do this. So step 1. So what we have is locate the element in the periodic table. So we want to locate the element in the periodic table and identify and write the electron configuration of its highest occupied energy sublevel. So we're going to identify and write the electron configuration. Of its highest occupied energy sublevel. So that's step 1. Step 2, we're going to look at to the left of what is written list all lower energy sublevels in order of increasing energy. Step 3, what we're going to do is for each filled lower energy sublevel, lower energy sublevel, we're going to write the number of electrons that fill that sublevel as a subscript. So are those numbers we were talking about in the subscript location. Fill that sublevel as a superscript. I meant superscript. Sorry if I said subscript. Superscript is the one on top. Then now we're going to do step 4. Confirm. So this is totally optional, but I do recommend it. Confirm that the total number of electrons is the same as the atomic number. So make sure that the electrons that you've written out is the same as the atomic number. So you'll always be correct if you do that. Okay, so there are some exceptions to this rule. And we're going to list them now. Exceptions. So there are things called interruptions. Interruptions appear among 3D electrons. So in the 3D level. And that's all we'll be talking about through the 3D level and nothing below 3D, because that's too much. Electrons so we have two exceptions: chromium is equals 24 and copper. So if you notice these two elements, there's two exceptions. That chromium is 4s1, so chromium is this. Its configuration is actually 4s1 and 3d5. And the reason it does that is because it's something called the Hund's rule. So it's better if you maximize all the d orbitals with singly occupied electrons instead of pairing them in the 4s2 orbital because of electron repulsion. But I don't expect you guys to know that. Just know that there's some exceptions for chromium, copper, and that you'll have to be aware of the correct electron configuration, but I don't expect you guys to know why. So in copper is 4s1, 3d10. And it has the argon shell. So it'll be you can write the whole thing out or just say argon, 4s1, 3d5, 4s1, 3d10. Okay? So okay, let's now try one ourselves. Okay, here's an example. Example for you guys to try. Please do it. Write the complete. All right, when we say complete, you cannot use the noble gas core. So you can't use neon core or argon core. You have to write the full electric configuration out. If you don't, I will probably take off half, maybe 1 or 2 points or half the points because you're missing that information. All right, so write the complete electron configuration. So you'll be able to use the periodic table. So don't worry too much about not being memorizing the electron configurations, because that's not the whole point. For coring. So coring is Cl, and it has a Z number of 17. All right, so let's do this one. Okay, so I'm just going to go through a step-by-step solution so we're all on the same page. So this solution will be long. All right. So let's go through it. So solution. Step 1. Position of the element. Is. Where is it? Group. So find out your periodic table, 7A, group 17, period 3. So what that means is the electron configuration. So the electron configuration of the highest occupied energy sublevel of coring is 3p5. So you can figure out that it's 3p5 by looking at a periodic table and counting out how many electrons it takes to reach the coring in the p block. Next, we have step 2, which is sublevels. Oops, backtrack. Sublevels having lower energies than 3p can be read across the periods. The periods from the left to right, in the periodic table. So we can, so you could do it like this way, 3p5. So then we could go backwards and read across the periodic table. So we have the 3s. So we have 3s just before the 3p. Then we go up a level, 2p, 2s, and then 1s. Or you can write as personally, I would not mind which electron configuration you use. So you could use the noble gas configuration too. Neon, 3s, 3p5. So I wouldn't mind. So I backtrack. If I wrote this type of question, you could use either one. But if I specifically say do not use the noble gas core, do not use it. But if it doesn't specify anything like that, you're free to use it. Okay. All right. So now we go to step 3. So we wrote out our basic configuration. Now we need to fill the sublevels. So step 3 is remaining sublevels need to be filled. Need to be filled. So a prefix, so not prefix, a filled two electrons, and a filled P has 6. And you can figure this out by just counting the number of elements in the S block and the number of elements in the P block till you reach the end, and you'll get these two values. And a filled P has 6. Okay. Oops. So we can write now our complete electron configuration by writing 1s2, 2s2, 2p6, 3s2, 3p5. Or as neon, 3s2, 3p5. I think I know what method a lot of students will do. The one on the right, short and simple and gets to the point. But you can use either if it helps you, mentally keep track of things. Okay. So step 4, let's check that our electrons equal our atomic number. So step 4, you simply check here and you just count the superscripts in your formula or in your electron configuration. 2 plus 2 plus 6 plus 2 plus 5. So it may be helpful to write that fully out so you can check, but you don't have to. So that's 4, 10, 17. So that is 17, which equals our atomic number. So it's a good check. You're good to go. Okay. Now let's do an example, another example. Now, hopefully we can write it out, quickly, but if you can't, just take the steps to look at the periodic table and do this example. So here's our active exercise for today. All right, I want you to develop, which basically means just write the electron configuration for cobalt. Cobalt. Oh, does not sound like a cool word. I like saying cobalt. It sounds really cool. Anyway, ignore that. So cobalt. So cobalt Z equals 27. So we're going to look at for cobalt on our periodic table and write the electron configuration. So let's start. So have your periodic table out and look for cobalt, CO, and then follow along. Try it first and follow along with me. All right. So step 1. We know cobalt is in the 3rd energy level, and the highest occupied sublevel is the D block. So step 1, we locate D3, 7, we count the number of electrons to cobalt, that's 7. So we get that answer. So now we're going to go all the way back to the previous sublevels leading up to the 3D7. So let's write them in step 2. Of course, you don't have to do it this way. If you could just figure it out by reading it first and getting to the cobalt, by all means do that too. In fact, that's how I learned how to do it. So there's 1s, 2s, 2p, 3s, 3p, then 3d. Oh, no. Let's take a step back. So 3s, so if you look at the periodic table, it goes 3s, 3p, then 4s, 3d. And the reason for that is that is from that first slide I showed you. 3ds are typically higher in energy than the 4s because the d orbitals are higher in energy than the s orbitals. So that's how the trend goes. So there's 4s. So you got to remember that there's 4s. And then immediately after the 4s, you get to the d block on the periodic table. So you know it's 3d. So you should always follow the periodic table and use that to your advantage. So if you're struggling with that, I would practice a lot using the periodic table and writing electron configurations. That's always a good way to help you understand this. So 4p, 4s, sorry, not 4p, 3p, 4s, then 3d7. Or if you do not want to write all that, you could say argon, 3d7. Not 3d7, sorry. Goes up all the way to 3p, and you have 4s, 3d7. Okay, hopefully everyone is still with me on this. All right, step 3, we now fill in the remaining electrons in the sublevels. So step 3, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d7. Or argon, much shorter, 4s2, 3d7. Now we check. Step 4, you can check. So we have 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 7. G equals 2. So the first one's 4, 10, 18, 20 plus 7, 27. So we have 27. So that's good. And that's our final answer. Okay. So hopefully everyone is kind of comfortable doing this. If you're not, just go back through the examples, look at examples on the homework, and you'll have lots of practice with this. So this is a very important concept. So I would study it because I'll definitely ask this on the midterm. And you can expect to see this in Gen Chem. They will focus on this particularly, and it's important to know because you'll have to write configurations for all sorts of things in future for general chemistry. So it's good to have a good foundation at the get-go. All right. So now let's talk about valence electrons. What are valence electrons? So valence electrons, you may have heard of valence electrons. They're also known as the highest energy or outermost shell electrons in an atom or element or ion. So valence electrons, they're the most important electrons because they are the ones that are involved in chemical reactions or chemical bonding. So let's talk about them. So they are the highest energy S and P electrons. In an atom. So the thing is, why isn't the 3D? Because sometimes the 3D orbital is higher than the 4s. Well, it turns out as you fill for transition elements in the D block, as you fill, like the first row is scandium, Sc, as you fill electrons in that D block, the energy levels between the 4s and 3D shift. because the energy and the electrons, once they occupy orbital, the attraction between the nucleus and the electron will kind of skew the electron, the orbital, to be closer to the nucleus, so they rearrange. And since when you start filling the d orbitals, there's less electron repulsion because of an occupied 4s2 orbital. The repulsion actually increases the energy above the 3D. So that's why we don't usually see the 3D, because it's usually not occupied, or when it is occupied, it goes lower. It goes lower than the 4s and the 4p. But if that doesn't make sense, we can also always talk about it later, outside in office hours or something. But valence electrons, the highest level, s and p electrons in an atom, which determine the bonding characteristics. So like I said about the bonding and chemical reactions, the bonding characteristics. So the bonding characteristics of an element. So next chapter, we will talk about bonding. So this is a preface to that. So it all connects. So for example, we have phosphorus. So example here, phosphorus, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. So we look at the highest occupied energy level. Highest occupied energy level is 3. Is 3. And we have, there are our 2s electrons. And 2p electrons. No, that should be 3. Sorry, that's a typo. Another typo. I will have to fix that on the slide. Sorry about that, everyone. And 3p electrons. This class only happens once a year, so I didn't have a chance to fix that error. So sorry about that. 3p electrons. So we have a total of 5 valence electrons. And the number of valence electrons actually it actually coincides with the group number. So for example, group 5a, that means every element in that group has 5 valence electrons. So it actually has connection to the groupings in the periodic table. All right. So now the highest occupied sublevels of all families of main group elements of main group. So this does not apply to the transition metals of main group. All families of main groups can be written as so N is the principal energy level, Sx, and then NPy. So the number of valence electrons is just the sum of the superscripts of X and Y. So they'll always have the same number of valence electrons, and you can always tell by the highest level. Number of valence electrons is the sum of X plus Y. Okay, so those are valence electrons, the outermost shell electrons in the element. Okay, so now let's go back to the lecture slide because there's an important table I want to show. So we see here that in our group, in our group naming, if you use the US notation, it can tell you how many valence electrons are in those group of elements. For example, here's my group numbers, and here's my electron configurations, and we can see here the group number will equal the number of electrons in the sublevels. 1, 2, 2 plus 1, 3, 4, 5, 6, 7, 8. And you see here that'll match almost completely. So you can use the group number to figure out how many valence electrons those elements should have as an isolated neutral element. For example, sodium has 1 valence electron, magnesium 2, aluminum 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7, argon 8. So we'll talk about what these symbols mean and what these dots means. That may come up on an exam, so it's be helpful to know how to draw them. But when you're drawing these dots, it's best to pair them up before you, well, not pair them up. Well, no, I'll talk about more about this. Okay, let's move on. So we're going to go back here. Hold on, let me just check the time. All right, a little bit over 10 minutes. So let's go back to our drawing board here. Okay, so we're going to go over, now we're going to go over, let's do another active exercise. It's important that we do these so we can understand what we're learning and get a feel for what's going to be tested. So active exercise here. So I want you to write, whoops, that was weird. Write the electron configuration. So this is a common question I ask for multiple choice. Write the electron configuration for the highest occupied energy level. Energy level for group 6A. So you get a periodic table, so don't worry, you don't have to memorize where they are on the periodic table. 16 elements. So we're going to look at our group 6A, 16, and see down the period which energy level, what's the highest occupied energy level for those elements. So we go to the group 6A on the periodic table, that's towards the P block, and what we see are, what we should get is this. So we want to write something like, okay, so we're going to write a generic configuration. So N S2 NP4. So it doesn't matter. So the thing is, so there's an N in front of it because it doesn't matter. Each element there, the highest level it will be whatever the sublevels in that level, it'll be 1, 2, 3, or 4, but it'll always have the same configuration: N2, NS2, NP4. So always have that generic, template electron configuration. And the only thing will change between the elements is what the principal energy level is, the value for N. So that is that one. All right. So now we're going to do another one. Identify the group whose electron configuration for the highest occupied energy level is NS2 NP2. So we want to go to, so we're going to look at, so the NS2 is filled. So we're going to look at our P block on the periodic table where there's only 2 electrons filled in the P block. So we're going to look at that group number for the group number for those elements. So we look at the periodic table. Do that really quick. We're going to look at the periodic table, and the answer we should get is this. Group, so that should be group 4, group 4A, or group 14. So this, the trick to doing these is just looking at a periodic table and find which group matches our electron configuration. So let's go back quickly to this first one here. I just want to make a note. So group 6A / 16 elements have 6 valence electrons. So we counted 6 from the group number. Valence electrons as indicated by the group number. First 2. So the first 2 must be in the s orbital. In the s, we just call it s level here. And the remaining 4 will be in the p level. So that is how we approach these types of problems. Okay. So for this part, we can ask ourselves, the sum of the valence electrons is, so sum of valence electrons is 2 plus 2 equals 4. And so therefore, the group is is 4A or /14. So using the group number is very helpful for determining the valence electrons and the electron configuration. We could link it to that group. Okay, so that is the active exercise. Hopefully that was okay for everyone. All right, let's see how much time we have left. Okay, we have a little bit less than 5 minutes. We're going to talk about, for the last part of this, Lewis symbols. So those letter symbols with dots around them, those are called Lewis symbols. So what they are, we can say they are diagrams. Diagram representing So this is also something I'd like to test. So a lot of people can get confused on this, so I would study it, study it well. Representing the valence, sorry, representing the valence electrons. And covalent bonds. Covalent bonds. We'll talk about what covalent bonds are. Bonds in an atomic or molecular species. So they are also called. They are called as electron dot symbols. So those electron dots around the symbols, those are the Lewis symbols. Electron dot symbols. Let's highlight this like so. So what elements like are called an octet of electrons? You may have heard of the octet rule. So that is what we refer to as the octet of electrons. So that means an atom wants to have an outer shell of 8 electrons. So let's highlight that too. So that's something important to know, like so. All right. So we can see here group 8A or 18, those are the noble gases. So helium, argon, neon, so the ones I mentioned. So group 8A or 18 atoms, where 8 electrons. Surround an atom. Valence electron configuration. Is like so, is NS2 and P6. So we see here that we have a filled S shell and a P shell. So that's a valence electron configuration of an octet of electrons when everything is completely filled. So here's an example. So we'll end on this, on the rest of this information, and we'll pick up on Tuesday. So here's an example. The electron dot symbol for tellurium. So tellurium is Te or Te, Te, Z equals 52. So we have a Z equals 52. So what we represent, we just represent the valence electrons on the symbol. So there is 6. So we do 1 dot here. And then we just continue pairing up the dots because each orbital can only have two electrons. So how do we know there's 6? Well, as tellurium, so we look in our periodic table, as tellurium is part of group 6A / 16, it has, all right, so that is our timer. It has 6 valence electrons. So that's how I expect you to kind of translate between going from valence electrons to maybe it's Lewis symbol or Lewis dot symbol. And that's how we could represent the element in its neutral state, or the neutral element on the periodic table. Okay, everyone, that is it for this week. Hopefully you guys stuck with the material. If it didn't make any sense, I would try the homework that goes over this so you can complete it and review and make sure you don't fall behind on the homework. The homework I'll probably extend till maybe next Thursday. So but please get started. The information we cover is vast, so I'm pretty sure there are not a lot of modules, but if there are, I would recommend starting early. Do not put it off, because that can result in you getting a score that is less than what you actually think you can do. But guys, have a great weekend. Stay safe, and I'll see you on Tuesday. All right, bye.